Hello, this is Burkhart. I'm going through the answer key for 3A, and let's just start a timer because I don't want this video to drag on and on and on. So let's just start that. All right, so Angela is in a stopped car at a traffic light. The light turns green and she accelerates. Sketch and label vectors for velocity and acceleration and net force on the car. All right, so using the drawing tool here, and she's stopped at the stoplight and she accelerates. And let's say she stopped at the stoplight. Force is going this way, and the acceleration is going that way. So how does Angela's body feel pushed? So she hits the gas and it feels like she's being pushed back, right? Why does she feel pushed back? Well, she's at rest, and according to Newton's first law, she wants to stay at rest until the car is moving underneath her, so she feels the back of the seat pushing her forward while her head remains at rest. Feels like something is pushing her head back. Oops. Now she approaches a stop sign. She slams on the brakes. Sketch and label vectors for velocity, acceleration, and net force on the car. This is not a free body diagram. So while she's rolling, she's got a velocity going this way, but now the force is that way and the acceleration is that way. So how does she feel pushed? It feels like she's being pushed forward, and the car is accelerating backwards, and the net force is back because the brakes are slowing it down. All right, now she's driving and she's going around a curve, and what we want to know is, oops. All right, so she's going around a curve. Now let's draw in so the velocity is this way. And so when you're going in a curve, you experience this inward force called centripetal force and caused by centripetal acceleration. So it looks like that. And so she feels pushed towards the outside. Feels like she's being pushed, this way, outside this way. And car's accelerating toward the center of the circle. The net force is toward the center of the circle. Okay. And so that was A. We're at 3 minutes. Let's try B. All right. So cars traveling along the road, air resistance can be ignored. All right. Or in the vacuum, you can breathe. All right, so for the following situations, determine if the car is speeding up or slowing down or staying at a constant speed and turning clockwise, counterclockwise, or not turning. All right, so here the acceleration is to the up and the velocity is to the right. And so what is happening here is that this is a constant speed, and it is turning counterclockwise because that makes the arrow go in, right? So if it's turning like this, right, counterclockwise, and at that moment its velocity is pushing forward, but its acceleration is inward. All right, how about this? So here we're speeding up, so speed increases. And how do we know that? It's because the acceleration is not perpendicular, it's off at an angle. So here we are turning clockwise this way, and we're speeding up. And that's why you see how the arrow is perpendicular to that right there. It's going like that. So that would be clockwise. And here we're going at a constant speed, and we're turning clockwise. This is just the opposite of the first one. All right, we're going this way. All right, so at that moment, the speed is this way and the acceleration is, I'm sorry, clockwise is this way. My bad. Messed up. And on the next one, we're slowing down. Speed is decreasing, and we're going counterclockwise. So what does that mean? Counterclockwise would be like this, and we're slowing down, and that causes the acceleration to move over to the right. Where are we at for time? We're at 5 minutes, so we're going to go ahead and stop. We'll call that 3A and B, and we'll start a new video for part C.